Hello. As we defined conditional distribution functions, we can define conditional expectations using them. So the idea is the expectations are defined based on the CDF. If you replace the CDF with a conditional distribution function, conditional CDF, then you can define conditional expectation like this. So if you assume the existence of PDF, then you may write it this way. Just replace the PDF with a conditional PDF. Everything is the same, but what I wanted to tell you here is, let's go back here. In this notation, x, it is a constant. It does not depend on x, right? So there is nothing you can change. So say expectation of x squared. Then the result will be, say, 1. Suppose that expectation of x squared equals to 1. It is not a function. It is just one number. It is just one constant, one number. There is no function. X is integrated out. So x squared provides the randomness, but after taking the expectation, it goes away. The randomness goes away, and it only has one number. Same thing here. When you define this conditional expectation, randomness is provided by x because this is expected value of x, conditional on y equals to y. So expected value of x given that y equals to y. So that means x provides the randomness, but it disappears. Its randomness disappears. So in the end, it is constant with respect to x. However, there is a room for change. So you may change y. For example, the expected value of x given y equals to 0 or given y equals to 1 could be different. So when you change this value, the expected value of x could be different. The conditional expectation will be different. So as a result, it is a function of y. It's obvious if you think it carefully and just say what it means, and then it is obvious. I cannot explain it any easier than this. So when you change y, then this value will change. That's the function of y. However, there is nothing you can change with respect to x, so this is not a function of x. You need to understand that. Then, let's think about this. Then the law of iterated expectation can be understood very easily. The expected value of g of x, simply say expected value of y, can be written in this way, right? The function of y times fy dy, right? And in this function, in the place of the function, I will consider the conditional expectation of y, or of x given y. So as I said, this is a function of y, so you can just put it as g of y, and then you may write it this way. The conditional expectation is again defined this way. So then, therefore, if you replace g of y with expected value of x given y, then it equals to expected value of gy. So you can write it this way using this result. And then gy can be replaced by this guy. So plug that into here. And then two integrations. You get this. And y will be integrated out. There is no y here. So if you integrate the joint distribution with respect to y, then it disappears. So in the end, you get simply expected value of x. Right? So this is the law of iterated expectations. And here, the most important thing here is that to understand the conditional expectation is a function of the conditioning variable. It's many people don't understand this, but kind of obvious. And independence. Independence also follows from the conditional expectation. So when x and y are independent, there are many interesting relationships, like expected value of multiplication of two functions can be split into different expectations. Or conditional expectation of x given y equals to unconditional expectation, right? I'm not going to explain in details. Proof is simple and also intuitively easy to understand. And what I want to emphasize here is we are going to, in our maybe in our theory, in many different models, we need to assume the independence. So the assumption is very powerful, and we assume that in many places. But there are three different forms of independence assumption, depending on the model. The first is that x and y are fully statistically independent. This is a full independence. And second independence type assumption is that the conditional expectation of x given y does not depend on y. So conditioning on y does not matter. So we say that this is a mean independence assumption. And the third form of the independence assumption is simply the uncorrelatedness. X and y have zero covariance, zero correlation. So if you compare these three independence assumptions, their role is similar in different models. Basically, they are implying the same intuition, but mathematically, obviously, they are different. Especially, this is the most strongest assumption, very restrictive. So you have to have perfect independence. But in the second assumption, it doesn't need to be a perfect independence, but the independence just need to hold with respect to this conditional mean. And finally, it's just covariance, which is kind of linear measure of independence. So if the first assumption is satisfied, automatically the second one is satisfied. And if second one is satisfied, automatically the third one is satisfied. So that means the first assumption is the strongest assumption, and the last assumption is the mildest assumption. So for an assumption, the milder, the better, right? The mild assumption is a better assumption because it is not that restrictive. The first assumption is the most restrictive assumption. So if you can use the third one, you don't need the first one. So third assumption is the better than the first one, if everything else being the same. Okay, that's a simple concept that comes again later. And one more simple thing to understand here is that probability, so far I have explained the expectation as a kind of following from the CDF. That is true, but you may view it the other way. Probability can be viewed as, the CDF can be viewed as a kind of expectation. But in this case, the function is a indicator function. So indicator function, which takes 1 or 0. If you use this function, probability can be understood as a kind of expectation. And so because of this, when I was a graduate student at Yale, I took some statistics department courses. There was a very old professor, very famous professor named David Pollard. To him, obviously he is a genius. He's a mathematical genius. To him, everything is too obvious, and he doesn't like those notations because to him, probability and expectations are the same thing. And so say to him, probability, expectation, and integration are no different. They are all the same thing. So he does not follow our notation. This is the common notation, but he threw away this notation and he made up his own notation because integration is enough to denote everything. So that is right. He was right, but the problem is he can process that kind of thought process very quickly. He's a genius. But as a student, when I take his class, I cannot understand. So is that a probability? Is that an expectation, or just a mathematical expectation? What's that? So it was so frustrating to me. I could not follow what he's doing there because he's switching between them like too quickly. And it was very fun. But I learned that better notation is better, but the best notation is the notation that everyone knows. So uh, yeah, so I cannot change anything. Like you are going to see a lot of kind of unnatural notation in the future and in my maybe in my course. I will tell you this is not natural, but I have no power. I cannot change notation by myself. So please understand. And final comment is about the comparison between distribution functions and expectations. I explained as if those two are the main pillars of statistics. Yes, they are. They are the most basic fundamentals, most important fundamentals in statistics and any kind of analysis of randomness. When you compare them, I can say that distribution functions are more fundamental basis, like mathematically fundamental, because the CDF is basically the basis. CDF is what we usually think as the definition of a random variable, but expectations are more convenient, more useful for two reasons. First, it is easier to interpret. So when I tell you about what is the say like what is your how good you are. So then if I'm curious about your academic level, then the easiest way is to look at your GPA. So that is the average grade. So like that, when I tell you what is the mean, what is the variance, what was the mean, like the average stock market return, or what is the variance in the stock market, then it delivers the basic information you need. However, probability is not like that. So when I say 30% of stocks have a positive return, okay, that's nice, but it's hard to understand then how big was the average or what was the volatility. So from one probability, the big picture is not drawn. It is just at about 1 point. So usually when in your presentation of the results, mean and variance are the most convenient way to deliver the information. And second, mild assumptions. So this is the flip side of this. Distribution functions are more fundamental object in mathematical definition. So that means when you impose restrictions on the distribution functions, that means you are imposing more restrictions on the more fundamental basis. However, say mean and variance are not complete information of the randomness. That means which may be a negative or minus, but at the same time it could be good because when you restrict the mean and the variance, you are restricting only some part of the distribution, not the whole probability distribution. For example, when you compare two examples where you assume epsilon is normal distribution, you are imposing a very restrictive assumption. Its probability distribution has to be a normal distribution everywhere. So very strong. But as a comparison, you may consider something like this. Expectation of epsilon is 0, variance of epsilon is sigma squared. Then it is less restrictive because mean and variance is not everything. It's not a full information. So in that sense, you can compare the distribution functions and expectations. So in the next video, I will start inferential statistics, review of inferential statistics. Thank you for watching the video. See you in the next video.